Hello everyone, hello my dear students. Here we go for the fourth quarter. We're gonna talk about the nature of the chemical equilibrium. We have to define the chemical equilibrium, explain the nature of the equilibrium constant, writing the chemical equilibrium expressions and carry out calculations involving them. Theoretically, every reaction can proceed in two different directions, forward and reverse. Essentially, all chemical reactions are considered to be reversible under suitable conditions. To know a chemical reaction in which the products can react to reform the reactants called a reversible reaction. To be more clear, a reversible chemical reaction is a chemical equilibrium when the rate of its forward reaction equals the rate of its reverse reaction, and the concentrations of the products and reactants remains the same, unchanged. State of dynamic equilibrium has been reached when the amounts of products and reactants remain constant. Both reactions continue, but there is not yet a change in the composition of the system. The system is static, apparently, but dynamic in reality. The chemical equation for the reaction at equilibrium is written using double arrows to indicate the overall reversibility of the reaction, as shown. The mercury oxide in the solid state is decomposed into mercury liquid and oxygen gas. This is the forward reaction. Also, the mercury liquid can react with the oxygen back to form the HGO in the solid state. This means that many chemical reactions are reversible under ordinary conditions of temperature and concentration. They will reach the state of equilibrium unless at least one of the two substances involved escape or is removed from the reaction system. When the products of the forward reaction are favored, there is a higher concentration of the products than that of the reactants and equilibrium. That's we say the equilibrium lies to the right. When the products reverse reaction are favored, there is a high concentration of reactants than of products at equilibrium. That we say the equilibrium lies to the left. In other cases, both forward and reverse reactions occur to nearly the same extent before chemical equilibrium is established. Neither reaction is favored, and considerable concentrations of both reactants and products are present at equilibrium. The equilibrium is a dynamic state, such that the product of the forward reaction favored lies to the right, as the following equation: SO2 reacts with O2 to give SO3 gas. Product of the reversed reaction favored lies to the left, as shown. The H3O reacts with the HCO3 aqueous, giving H2CO3 plus H2O. Here we can recognize that the larger arrow indicates the favored direction for the chemical reaction. If neither reaction is favored, this means that the forward reaction, which is the H2SO3 aqueous plus H2O giving H3O plus HSO3 negative, having the same credibility of the equation when the backward reaction takes place, reacting the hydronium ion H3O with HSO3 aqueous to give back H2SO3 aqueous plus H2O. The equilibrium expression Na plus Mb gives Xc plus Yd. Initially, the concentrations of C and D are 0, and those of A and B are the maximum. Over time, the rate of the forward reaction decreases as A and B are used up. The rate of reverse increases as C and D are formed. When these two reactions takes place equally, when these two reaction rates becomes equal, the equilibrium is established. As we can see the reaction rate over the time. The forward reaction, which is A plus B giving C plus D, decreases at the same time. The reaction between C and D to gives reversely A and B increases. During an interval of time, the two chemical reaction rates became equal. The forward rate equals the reverse rate. Here we reached the equilibrium state. A ratio of their concentrations should also remain constant. The equilibrium constant is given the letter K. K equals the concentration of C, which is the product of the forward reaction, also it is the reactant of the backward reaction, times the concentration of D divided the concentration of A times that of B. But keep in mind that each is raised to the power of number of moles. Again, to be repeated, each is raised to the power of number of moles in the chemical equation, in the balanced chemical equation. Here is X, Y, also N and M. The constant K is independent of the initial concentrations. It is dependent on the temperature of the system. The equilibrium constant is the numerical value of K for a particular equilibrium system is obtained experimentally. If K is equal to 1 at equilibrium, there is roughly equal concentrations of reactants and products. The value of K is small, the reactants are favored. The large values of K indicates that the products are favored. Only the concentrations of substances that can actually change are included in K. Pure solids and liquids are omitted because their concentrations cannot change. How to determine the equilibrium constant for the reaction? You have at first to write the balanced chemical equation, to write the equilibrium expression, and to complete the equilibrium expression. The constant K is the ratio of the mathematical product of the concentration of substance formed at equilibrium to the mathematical product of concentrations of reacting substances. Each concentration is raised to the power equal to the coefficient of that substance in the chemical equation. The equation for K is sometimes referred to as the chemical equilibrium expression. For example, the H2I2HI equilibrium system. The rate of reactions between the hydrogen and iodide vapor in a sealed flask at an elevated temperature can be followed by observing the rate at which the violet color of iodine vapor diminishes. The iodine vapor is having violet color, and this color is being diminished as long as the reaction between the H2 and I2 proceeds. The color fades but does not disappear completely because the reaction is reversible. So hydrogen iodide decomposes to reform hydrogen and iodine. The constant color achieved indicates the equilibrium exists among hydrogen iodine and hydrogen iodide. The forward reaction rate decreases and the reverse reaction increases until we get the forward rate equivalent to the reverse rate. The net chemical equation is H2 plus I2 giving 2HI. The chemical expression is K equals the concentration of the products of the forward reaction, HI, over the concentration of the reactants of the forward reaction, H2I2. Each is raised to the power of the coefficient, which is 2, and here power 1, here is power 1. The value of K is given at constant temperature. For example, for this value of concentrations, we got K 54.46, 1.41, and so on, so on, so on, so on, to give 54.33, which is at 425 degrees Celsius. The balanced chemical equation for an equilibrium is necessary to write the expression. Once the value of the equilibrium constant is known, the equilibrium constant expression can also be used to calculate the concentrations of reactants or products at equilibrium. Here we go for sample problem. An equilibrium of mixture N2, O2, and NO gases at 1500 Kelvin is determined to consist of 6.4 times 10 power negative 3 mole per liter of N2, 1.7 times 10 power negative 3 mole per liter of O2, and 1.1 times 10 power negative 15 mole per liter of NO. What is the chemical equilibrium constant for the system at this temperature? Here are the given concentrations. The unknown is K. Okay. Let's write the balanced chemical equation N2 plus O2 to give 2NO. Therefore, the K equals NO power 2. This power 2 is referred by the coefficient here. Divided by the concentration of N2 times O2. Just you have to substitute as the following. You'll get that the K equals 1.1 times 10 power negative 5. That was section 1, the nature of chemical equilibrium. Stay tuned and get ready for your homework. Check your LMS. Bye bye.